So without further ado, okay, so in the first part, I'm going to define what I mean by heat map and how we build it from reverse geocode logs. In the second part, I will discuss contrast enhancement, culminating with a discussion and description of histogram equalization in Spark. And then the third, I will talk about kernel-based image processing, which is basically convolution of an image with a matrix. And I will describe an implementation of Gaussian smoothing in Spark. However, the method I describe is general, so any kernel-based method can be implemented this way. And so, as I say, the motivation here is for noise removal. So I should talk a bit about the company as background. So I work for Here Technologies. We're best known as a maps company that's been around a long time in digital maps, at least 30 years or so, in various incarnations. Today we still have a map as our major product, and moving forward, we're evolving the map into a high definition with high definition layers, and this type of map actually is going to power or work will be a prior for all kinds of autonomous situations and vehicles. It's actually a major part of the business. I work in another segment of the business, which is platform. Today here is branded as like the open location platform, and specifically I work in the places and address search area, and we have map search and address search, autocompletion for these, and reverse geocoding. So I show you an example here of or a visualization of what address search might be or geocoding. And as I mentioned, reverse geocoding is important, especially for this talk, because the heat maps are being built from reverse geocoding logs. So just so we have a foundation here, so you submit a latitude-longitude pair, which is a geocode, and get back some human understandable location. And so in this case, in the response, you can see Mitte, Berlin, as the sort of the district that's being responded with. And one of the major use cases for this is tracking of assets, that sort of thing. And we actually have a lot. This is like one of our major, like heaviest used services. Something like several billion transactions a month. So what is the heat map? So specifically what this is, we can take coordinate space, so latitude and longitude. So latitude is a north-south bearing, longitude is an east-west bearing. So it's the latitude's the y and longitude's the x. And we can grid this with cells that are square, and then accumulate geocodes. And we do this just the way you think. So we count all the geocodes that appear in the cell. This is a very high resolution image. So each latitude longitude increment is like 100,000th in extent, so width and height. So we have these squares. And we aggregate in such a way that we have basically a data frame, a latitude, a longitude, and a count. So this is the data structure that we're using. So it's pretty simple. One of the caveats, of course, is that area varies by latitude. So we model the Earth as a sphere. Sphere is actually no oblate sphere, but working with a spherical model is perfectly appropriate in this case. And because we have this very well-understood model, we have like all kinds of closed formulas for area. And in particular, if you do the calculus, you get a nice area formula in terms of forms of latitude, and you can plot this inverted parabola here. So I show proof that places like, for instance, Bangalore in India have cell areas that are almost twice what they are here in northern Europe. So it's important that we take into account area to remove bias from the different cell areas. It's very simple. We just compute the area at the latitude and get a density, right? So count divided by. So it's, as you can guess, this is not a conventional image. I like to think of it as sort of like a scientific image, like an X-ray or a thermal image. We also don't have sort of like a fixed pixel. This is actually an issue that histogram equalization addresses, so the counts can be whatever. The image is extremely sparse, so while there are almost 7 trillion tiles, only some very small percentage, like less than 1%, are actually occupied. And I give an example here comparing it to like the highest resolution TVs you can buy. So it's when I show you pictures of this heat map, it's the images are all rastered, and I do this also in Spark, but that's a standard, like the imperative implementation more or less goes over the same. So so the heat map, the data that I've described to you is actually really important, and we use it in our service. It's not something we look at, but it's used in our autocompletion service, and I have a picture of it here. So it's used in 2 places. One is in our early termination logic, and the next is in re-ranking of the results. So for people who don't know, you type in tokens, you have an inverted index, and when you in the prefixes where they're indexed, you have already pre-sorted, like top K results. To do this sorting, you need some kind of some ordering, right? So the way we do that is we use a heat map derived feature, and then we use that feature again in a re-ranking model. So if you take the histogram, if you take the heat map and just like visualize it without after accounting for area and all that, and just look at it, you get a black image. This is mainly because the histogram is super skewed. So I've plotted on the left an image of the histogram of a data set taken over a month, and it looks like a trivial, like there's nothing there, right? But when you zoom in, you see that actually, yes, there is something there. It's super concentrated between like 0 and 5. So the technique we're going to use is histogram equalization, and the idea here for contrast enhancement, the idea is to take the histogram we have and stretch it out. So we're basically matching it to the uniform distribution. And this is a point-wise image processing algorithm, right? So we don't care, we're transforming each pixel by a function. We don't care about what's happening in its neighborhood. And so to understand this, basically what we're doing is the solution to it is sort of mapping into the percentile ranks. And the way I like to explain this is like, say you have 2 cohorts of test takers, and they have maybe different tests of different, the highest score is different or something like that. How would you compare them? Well, think of any standardized test you took. You had probably a raw score and like a percentile rank, like top 20% or 90 percentile or 80 percentile of test takers or something like that. So this would be a way to compare between cohorts of test takers or something. So that's essentially what we are doing here with our pixels. So specifically, we build the histogram and then sort of sum the area. Well, we actually compute the CDF. So we take the input luminance, or the density, look up the value of the CDF, and then multiply by some number you choose. So n here is a constant. Sorry. So this is a result, and I will show you the image associated. But this is on the left-hand side, you have the histogram and the input image, and on the right, you have the transformed. And you can really see that it's been stretched out. So here I'm comparing. So on the right, you have the nice sort of histogram normalized image. So you can see it's really sharp, nice to look at. I've compared it here to the log scaled version. So the log scaling is also another pointwise processing algorithm. I shouldn't say algorithm. I mean, so basically you just apply like log to the pixel, and this is a common way to actually increase contrast, but histogram equalization clearly does better. Since we have normalized pixels, we can do comparison. So we're comparing apples to apples. Here you see an image of England from different time ranges. So so we're subtracting a recent time frame from an older time frame. And so we can take something like this, or a difference, and show it to an analyst, for instance, and they have a meaningful image to look at and say, oh, we can say these are really areas where we've seen reduction in usage, and likewise with the hotspots. So how is this implemented? It's mainly through map operations on data frames. So we do a map operation to get a density. This gives us the heat map that accounts for area. And then because we don't care about the neighborhood, we just apply a function. So this is just a map operation. The function here is a CDF, which we build in another step. So separately, we build the CDF. So the way we do this is take the heat map with the densities, and we just use group by. So we can use simple data frame API SQL operations, so histogram on the density, just the density column. We accumulate locally, or collect locally, accumulate to build our CDF. And importantly, we have to broadcast the CDF. So this is what gives us scalability. So recall that broadcast means you sort of ship the variable to each worker instead of just keeping a local array and sort of with every task kind of transmit that CDF. If the CDF gets really big, then you'll have problems. And so the way we represent the CDF after all this processing is you'll have, it's an array, so you'll have a bin, an array of like a pair, so the left bin and like a count. And so then to evaluate the CDF at some density value, all we do is a lookup. And the lookup is basically done using a binary search. And a binary search and linear interpolation. So this is, and the only maybe point I should bring up is that, again, the CDF, the representation we have is sparse. So some notes about histogram equalization is that if you have high or low signal to noise ratio, then or rather if you have a lot of background noise, the histogram equalization doesn't know anything about it. It doesn't distinguish noise from signal. It doesn't know anything about that. So noise reduction is really important. And histogram equalization does well, or seems to do well, on scientific-like images. Often images that are just one channel, thermal and X-ray images, for instance. And so this motivates the next and final part of this talk on spatial processing. So I'm going to describe kernel-based image processing, and in general, this is what we're doing is instead of transforming the pixel by some function of just the pixel, then what we want to do is transform the pixel by a neighbor of a function applied to the neighborhood. So examples of this are mean, median type filters, and also there are sort of derivative filters, for instance, that are used in edge detection, segmentation. I'm going to describe Gaussian filtering, Gaussian blurring. I wanted to say that it's often important to do noise removal. For instance, even not just because it's an important pre-processing step, and like for instance, if you're going to run like a Laplacian filter, like kernel filter over your image, that operator is inherently like noise sensitive. So you would want to Gaussian smooth your image beforehand, even prioritizing detail over noise removal in that case. So the way you would do this in the imperative way, so like this is a standard. There are implementations for this in C++ through OpenCV and ITK, if people know that library. But basically, the idea is really well known. You slide your square window, and I've highlighted an example like kernel window, which is a 5x5 square around the pixel of interest here. So you slide the kernel window over the image, iterating pixel by pixel, weighting each pixel in the neighborhood around the pixel of interest, summing, and then writing that to an output buffer. So this is what I said, sort of written out in sort of math notation. The result I will show you is based on this specific kernel. It's a standard Gaussian with sigma 1, or standard deviation 1. You can think of the indice, the h here as the kernel. You can think of it taking offsets. That's how I'll refer to it from here on. And we compute the transformed pixel by doing a kernel application and doing a summation over the window. But we can implement this with the group by. I'll say more about the algorithm and how it's adapted with data frames. So we first have to identify all of the new pixels in the sparse smoothed image. And we do that with what I'll call an explode operation. So there is like an explode function in the API. But what I did was literally map a row in the heat map to a list of other types. But in this way, we can get all the new pixel locations in the sparse smoothed image. Once we have that, I'll describe, we have to identify a certain type. And after that, we map over the exploded data frame to do the kernel application. And from there, we just do this group drive, which gives us the final pixel value in the sparse smoothed image. So when you explode, you can like think of it as every pixel in the input heat map knows its a neighborhood. We know how big that neighborhood is, so it's easy to identify the coordinates in latitude and longitude. So we've done that, and we get all of the new locations, which I've highlighted here in yellow. So we can tell the smooth image is going to be larger, like a lot bigger actually, but still sparse. But being a neighbor is reciprocal, right? So we can turn these arrows around and we realize, okay, that the neighbors point back to, we have the neighbors, which are, again, every pixel in the smoothed image, and I'm referring to the image on the right, pointing back to always its non-null neighbor. So without doing any transformation on the exploded data frame, we automatically have a window around, or at least we have in the data frame, not contiguous, but like in any in the data frame, we have any pixel in the smoothed image, which or non-null part of the sparse smoothed image, which may or may not be, again, in the original heat map. We always have a pointer from it to its non-null neighbor. So we have, and I say it here, so so the exploded data frame, you know, the pixel index exists in the exploded data frame if and only if it has a non-null neighbor. So we're not getting like pixels that won't be there. So this is specifically what the exploded data frame will look like. And we take the first row, so you take the first row, and that's, and we map to a type that has the offsets, the neighbor, and the original value. So the value being mapped from in the heat map, so 120 in this case, is repeated. So the neighbor values are all of the non-null parts of the transformed image, and these offsets and the original value allow us to do the kernel application. And so that's it, right? So we explode and identify all parts of the transformed image, the smooth image in this case, and identifying sort of the right data. We can put a kernel around every part of the pixel, non-null pixel in the transformed image. And then after that's pretty simple. We just do a kernel application by doing a map, grabbing the offsets, putting them into the kernel matrix, multiplying with the original value, and then grouping by, so that the group by is the sum. And so I have an example here of Frankfurt with and without blurring, and you can see that we have lost some sharpness, but we get some brightness, and you actually see some areas like some roads that were maybe not highlighted before. So there definitely is noise. There are sources of noise in our data coming from, these are all geocodes coming from GPS devices. So Gaussian smoothing is a way to account for this. Right, here's another example of Berlin with and without smoothing. So yeah, we consistently have, at least in these two examples, you see more sort of brightness around the, Mitte sort of center of the city. Okay, thanks. Appreciate your time, and again, I'm Arvind Rao from Here Technologies.
Thank you, Arvind. We've got 3.5 minutes. If you have any questions, please, there are 2 mics towards the end of the aisle. Please make your way towards it so we can actually get your questions on the audio. Any questions for Arvind? Oh, we have one question. Thank you.
Well, at the beginning, floats are, so the latitude and all these coordinates are floats, but you group by another. So do you, say, before make it like integer or fixed point? So how you group by on floats? That was my question.
How do you do group by?
On floats, yeah, so you mean the geocodes?
Yeah, right. Because it's, yeah.
So that is in part a good point, because if the data set that you're working with is really, really large, you should care about the type. You can actually reduce the sort of footprint of the image. I didn't have to do anything special to do group by on floats, or even you could just group by on the 2 columns by just specifying them. So there was no difficulty. Did I answer your question?
Well, actually, that probably
We can take it offline.
We can talk afterwards.
Yeah, let's talk it offline. We give somebody else a chance who actually has a question. If you don't have any questions, then please give a warm welcome to the speaker today, Arvind Rao.